Okay, good afternoon. So we are starting a slightly different thing today. Up to now, we've done stuff that in some ways is descriptive statistics or maybe an extension of descriptive statistics. Regression is a little bit of a mixture maybe of descriptive statistics and data analysis. Today we're going to start on probability. So the handout is on BSpace if you want to look at it. You don't need it today. I mean, if you've looked at it, great. If you haven't, I'm going to describe everything that's on it. This roughly mirrors what's in chapters 13, 14, 15 of your book, but slightly different notation. And I'll do just a little bit more than what the book does. So the handout kind of reflects that little extra bit more. OK, so probability, I'd like to kind of introduce by just doing sort of the simplest probability problem there is. What's the chance? I flip a coin. And I want to know what's the chance it lands heads. OK, so what's the answer? 50%, or you might say 1 and 2, 1/2. OK, either one is a perfectly reasonable way to answer it. And I think most people know that on some level. OK, so intuitively or whatever, you have some idea of what chance means on that level. But I want to be a little bit more careful with what I mean by chance. So when I say this, when I say there's a 50% chance it lands heads, or if I say the chance or probability it lands heads is 1/2, what I mean is that in the long run, if I flip the coin over and over again, I expect the long run proportion of heads to be close to 1/2. So there's a couple things I put in parentheses there. You could sort of read the sentence with or without them. Long run meaning like if I flip the coin lots and lots of times, like millions of times, billions of times, I expect the proportion of heads to be close to 1/2. Now, it won't necessarily be exactly 1/2, and that's something we'll talk about more later, but with this long run idea, it should be very, very, very close to 1/2. If you flip the coin enough times, your proportion of heads should be kind of extremely close to 1/2. So that's what I mean when I say 1/2. You expect the proportion. So you can expect the proportion to be 1/2, and it should at least be very close. OK. Now, part of the reason why I write that slightly more carefully is that I think in English we use chance in a sort of casual way. So we say things like the chance it'll rain tomorrow is 50%. OK, and I don't really mean the same thing when I say the chance a coin lands heads is 50%. Here, I really do mean that I kind of have in mind that I could repeat the coin toss over and over again. I might not want to flip it millions of times, but in theory, I could. And I should observe some proportion of heads. That should be close to 1/2. When I say the chance it rains tomorrow is 50%, I'm not really talking about chance in the same way. Okay? And so I'm not really talking about it as a statistician or a probabilist would talk about it. At least the way that most statisticians would talk about it. You might think of that as kind of a subjective probability or subjective chance. You can't repeat tomorrow over and over again under the same conditions and see what proportion of times it rains. Okay? So you can't really apply the same idea of repeated coin flips to the chance it rains tomorrow. So we won't really talk about things like that. I won't talk about I don't know, the chance the Warriors will win the next basketball game or something like that. It's not something you can repeat over and over again under the same conditions and see what percentage of times the Warriors win a basketball game or something like that. Okay, so because of that, like I say, we'll be a little bit careful and try to stick with examples where it can kind of reasonably be repeated over and over again. So a lot of the examples I'll talk about are with coin tosses, die rolls, deck of cards. These are situations where it's easy to imagine how we could repeat it over and over again. Shuffle the deck again, do it again. Shuffle the deck again, do it again. Die rolls also, sort of, you could repeat it over and over again. So some of the examples will have a sort of kind of a gambling context. Hopefully that doesn't bother anybody. But it's sort of a nice context to talk about a lot of these kinds of problems with chance. Okay? And this is called, this sort of definition is what's called frequency theory. And it's the way that your book kind of defines probability, and it's the way that most statisticians or probabilists talk about probability. There are some statisticians and probabilists that accept a more kind of loose definition of probability. So I sort of want to mention that you might encounter people in your life, possibly, that are perfectly comfortable talking about the chance it rains tomorrow in a kind of careful, rigorous way. But we won't really do it in here. We'll sort of restrict ourselves to cases where it's reasonable to repeat it over and over again under the same conditions and think about this proportion. Okay, so I want to talk just a little bit about the 1/2 and where that comes from. And I'm gonna outline some things in the same way that they're outlined on the handout. If you don't have the handout, it's fine, but I'll just use the numbers in the way they are in the handout. So the way the handout is organized is that the beginning of it kind of defines a little bit of notation, and then most of it talks about what I think of as kind of tools or rules for solving probability problems. If you have some event that you want to find the chance of, there are different ways that you might approach different problems, and I kind of view them as tools. This part of the course, I think, so I guess for the beginning of the course, a lot of the way you might think about doing problems is to try to think, okay, what sort of problem is this? How does this fit in to things I've done before? What formula should I use? Maybe something like that. This part of the course, I think, is a little bit, I don't know, kind of more subtle, or there might be different ways to solve a problem. So you sort of have these tools at your disposal, and sometimes some tools will be easier than others. Sometimes more than one will work, and so it's a little bit more fluid, I guess, in a way. It's not as like just memorize formulas and figure out when to use them. You have to be maybe a little bit more creative or a little bit more sort of try one thing, see if it works, see if it helps you. If it doesn't work, try something else. Okay, so the first one is what's called equally likely outcomes. So if all outcomes are equally likely, the chance an event happens is the number of ways it can happen divided by the total number of possible outcomes. Okay, so applying this to my little example with a coin toss here, there are two possible outcomes, and they are equally likely, right? And actually what tells me that in that problem is that it's a fair coin. The word fair means the sides, the possibilities are equally likely. So you'll see me use the word fair with respect to a coin, and you also see me use it with a die. So a fair die means all the faces, all the sides are equally likely. Sometimes I might leave it out. In general, I don't think I'll do any examples with coins that aren't fair or dice that aren't fair. So if I don't specify, I mean that it's fair. So if I talk about tossing a coin, I mean a fair coin. Okay, so 2 possible outcomes, heads and tails, and 1 way to get heads. So that's 1 way to think about that. You notice it's not enough to just say, like if I said, okay, there's a 1/2 chance of a coin landing heads. If I asked you why, you need this bit. Their outcomes are equally likely. A common response would be, well, it's 1/2 because there are 2 possible things that could happen. There's heads, there's tails. So you want to at least, realize that it's important also that they're equally likely. Okay. Okay. Let's see. Yeah. So I'll do one more just really quick, fairly simple. I kind of want to, I'll give you mostly simple examples to start with until we get most of the tools and rules set up, and then the examples will get a little bit more complicated. So one more easy one. Roll a fair die. Chance it lands 6 is what? So when I say die, I also mean it has 6 sides, not any kind of fancy Dungeons and Dragons dice or anything. This is a presumably fair die. So this, oh, I got a 6. So what's the chance it lands 6? 1/6. Again, 6 possible outcomes. One of them is a 6. Okay? So 1/6 chance. Okay. So yeah, so that's just another quick, simple example of equally likely outcomes. Like I say, we'll do some more complicated ones once I get a few more things down. The next one, actually, I'm sorry. I want to, all right, so this is equally likely outcomes. I want to do a little bit of the notation part of the handout. So this is tool or rule number 1, and just a little bit of notation to allow us to write things more easily. The capital letter A I'll often write as an event, okay? Represents an event, kind of generically the way you might think of, like, if you're doing algebra, you might use a lowercase x to be a variable, just kind of abstractly. So an event which may or may not occur. And we'll think of it as sort of fitting into this context of we could try it over and over again, and sometimes it would happen, and sometimes it wouldn't happen. So we could think about the probability of an event, and I'll write that as this capital P of A. So read that as probability of event A. Again, this is to some extent, this is just to provide us with some shorthand so I can write things more quickly and easily. The book doesn't use this kind of shorthand. The book usually writes things out in sentences with lots of English words. Most books that treat probability use this notation. So to some extent, I'm telling you this so that you can feel comfortable looking at the way that other books might be written. And also, like I said, just to make it a little bit easier to write things down. OK, so that's that. And one more thing I wanted to write down is this. A with a C, kind of superscript C, is we read that as a complement. Complement. And that's not like a compliment like, hey, nice dice. It's like a compliment like everything else. Okay, it's like the other stuff. So this is itself an event, and it's the event that the event A doesn't happen. Okay. So you think of the word. That's not a really common word, but like I say, it's the complement of the event. It's the other stuff. Okay. So let's think about that in terms of what's called a Venn diagram. Again, so the Venn diagram is actually not on the handout and not in the book, but I sort of like to talk about it. And I think it's pretty intuitive. I'll never test you on anything with Venn diagrams, but I think it's a nice way to give you a visual picture. It's a little bit like a histogram in the sense that the total area is 100% or 1. Now, when you think about the chance as being either 50%, 50% or 1/2, you can write down chances and do chances in either notation. It's a little bit more common to use fractions, okay? But you can think of it as a percent if you want. Thinking about fractions, then, like I say, the total area is 1. So total area is 100% or 1. And like I said, that's sort of like the way you think about a histogram, is having total area 100%. And in a histogram, when you think about total area 100%, you sort of know that everyone is somewhere, right? Or everything that could happen is somewhere in that picture, since it's all 100%. Same basic idea here, that this represents everything that could happen, right? In just a very abstract way. You kind of think about it as like picking a point at random from somewhere in this rectangle, okay? Every point is, you might think of as equally likely. Okay, so let's draw in here a little bit. If I have an event A that's like that, okay? So essentially what I'm saying is that if I pick a point at random, if I land inside the circle, then event A happens. If I land outside of the circle, event A doesn't happen. So that's A complement. It's everything outside of that circle. So you can then think of the chance or the probability of A as being like the area of that circle. Okay? So the total area is 1. So like my chance of getting in this circle is sort of the area of the circle divided by the total area. But since the total area is 1, I can just think of it as the actual area here. So probability of A equals area of that circle. Okay, any questions about that idea, that framework? Like I say, it's not, the Venn diagram is not super important, but I think it's a nice way to give you kind of a visual way of thinking about probability in terms of areas. And it leads us naturally to the next sort of rule, which is complement. Yeah, you can call it complement rule if you want to give it the name rule. And it says that the probability of event A is 1 minus the probability of the complement. Or if you want to think about things in terms of percentages, you could think of it as 100% minus the probability of the complement. And this is an idea that you use pretty frequently when you deal with the normal table, right? With a normal table, you think, just you draw as a little aside, total area is 100%, the area in the middle from the normal table, then the area on the outside is 100% minus the area in the middle. So this is basically the same idea. You want to find the chance of everything else, take 100% minus the chance that you have, that you know. Okay, so if it's easier to find the chance of the complement, that might be an easier way to get at the chance of an event itself. Okay? So like I say, you can also write that as 100% minus the probability of A complement if you want. You can reverse them and say the probability of A complement is 1 minus the probability of A. All of that, I think, is pretty clear and intuitive if you just think about this picture. Okay? Total area has to be 1, so if you wanted to find the area, the chance of A complement, well, you could do 1 minus the probability of A. Or the other way, the way I have it written, or you could think of it in percentage terms if you wanted. Okay, any questions about that? Okay, so just a really quick example for dice. This is an example where it's simple enough that you could really do it either of these ways, I think, before I started talking about probability. The problem the chance I want to find is for a fair die roll, find the chance the roll is 5 or less. Okay? So you could just think about that using equally likely outcomes, okay? And you just count, right? There are 5 ways to get a roll 5 or less. 1, 2, 3, 4, 5, 6 possible outcomes, so the chance is going to be 5/6. You could also, if you wanted to, if this was like confusing for some reason, that it'd be hard to count those things or something, it might be easier to think about this as the complement of rolling a 6. Okay? So this is equal to the complement of So if finding the chance of rolling a 6 is easier to think about than this event, you can do it that way, and you just get 1 minus 1/6 is 5/6. Okay, so like I said, this is simple enough, I hope, that either way makes sense. You could think about it either way if you wanted. You could either do it, like I said, just by counting equally likely outcomes, 5 ways for it to happen, 6 total possible outcomes, or you could do it by using the idea of complements. Okay, any questions on that? Okay, and there are cases where this is much easier to think about the complement of an event rather than the event itself. Okay, so I want to mention something about this complement rule in the way that the book treats it. So if you're reading the book discusses this as thinking about opposites. I sort of don't like using the word opposite. Now, the word opposite is it's sort of a more common word in English, but I think it's not actually quite. The problem with English is sometimes it's a little bit vague. And for example, if you think about the opposite of rolling a 6, you might think the opposite of rolling a 6 is rolling a 1. And that's not what we mean when we're talking about this idea. We're talking about everything else except for the event. Or think about the chance that the event doesn't happen. So in that sense, the opposite or complement of rolling a 6 is not rolling a 6. Okay, so I just want to point that out, that if you think about opposites, it can sometimes be a little bit confusing. But the book generally talks about this in terms of opposites. But the use of the word opposite in English is sometimes a little bit different than the use of the word complement. Okay, questions? Okay, so one more thing I want to define, and then, so maybe I'll just talk to just a bit big picture about the handout. The handout has a total of 5 rules. I'm going to do 3 of them. I've done 2 so far. I'm going to do a third one, and then do a little bit more in terms of examples. I think at the end of lecture today, I'll have time to get to the 4th thing, and then next Tuesday I'll finish up. I'll finish the 4th thing and the 5th thing. Okay? I think that'll all work. So before I get to the 3rd one, though, I want to define one more thing, which is conditional probability. Sort of has a fancy name. What this means is the chance of one event given that another event happens. And I'll write down a notation for this. Okay, so this vertical line here, you read this as given. So you read this as probability of event B given that event A happens. Oops. Happens. Okay, so that's like living in a universe where we know something already happened, okay? So if I wanted to talk about, let's say I roll 2 dice. 2 dice. And I could roll them in order. I could roll the red one first. And suppose I want to find the chance that event B is the sum of the two dice is equal to 2. Okay, so that can only happen if they're both 1s, right? And event A is the event that the first die, I'll say red die. The red die is a 1. Okay? So event B, the only way that can happen, like I said, is if they're both 1s. And essentially what the probability of B given A is in this situation is this is like the probability of getting the sum to be equal to 2 if this is sitting in front of me. So I already know. I'm given that the red die is a 1. That's already happened, already finished. Now I can just think about the probability that the blue die lands 1. I still need that to happen. So one way you might think about this is there's like a hurdle that's you've already gotten over. So this event A, getting the red die to be a 1, that's already happened. I don't need to worry about it. Now, in order to get the sum of the two dice to be a 2, I just need the other one to land 1. So you might think of this as now the probability that the blue die is a 1. Okay? Because like this has already happened, right? The A event has already happened. So blue die is a 1. So that's 1/6. Okay? So, questions about that? Okay. So that, like I say, is a little bit new notation to think about this thing where I can write the probability of one event given that another one's occurred. So yeah, I sort of think of this as sort of altering your universe in some way, that something's already happened. Okay. So that gets us to what's called the multiplication rule, the third tool or rule. So the multiplication rule says actually, well, I'll write this way first. It's used when you want to find the probability that two events both happen, A and B. So the probability two events both happen is the probability of one of them. And it doesn't really matter which one you choose first. A and B is the same as B and A. Probability of one of them times the probability that the other one happens, given the first one happens. Okay? So if you want to think about our little example here, if you wanted both these events to happen, the red one is a 1 and the sum of the two dice is a 2, you could think of it as, first of all, you need the red one to roll a 1, and then you need to get the sum of the probability of the sum of two dice is 2, given the first one's a 1. You can think about that, okay? So in our example, okay, so I'm still thinking about those same two events there, A and B over there. And I'll just write it out a little bit in English. Right? It's this, right? Probability of A is the probability that the first, or the red die, is 6, times the probability that the sum equals 2, which, another way of saying this is that they're both 1s, right? I'm sorry, 1. Red die is a 1. Okay? Red die is a 1 times the probability that the sum is 2, given that the red is a 1. So essentially, this last part is just the probability that the blue one's a 1, right? Just like I said over there. Okay. So this is going to be 1/6 times 1/6. Okay. Or if you want 1 out of 36. And maybe now is a good time to just mention that I don't really care if you leave your answer like this. 1/6 times 1/6 is OK. The reason I don't really care is that I really like doing probability problems. What I really care about is how you're thinking. I don't really care about getting a numerical answer or a decimal answer so much. I hope that you can all reduce fractions and do stuff like that. But I don't really need to see you do it. If an answer is 2 out of 6, then it's clear to me that if you write 2 out of 6, it's clear to me that you're thinking of 2 possible outcomes, so two ways that it can happen out of 6 possible outcomes. If you write a third, it's still right, but it might be a little bit less clear to me what you're thinking. And so reducing fractions is sort of, like I say, kind of optional. If you get the right answer, there's no problem either way. If you get the wrong answer, it might be harder to give you partial credit if it's unclear what you're thinking. So if you are gonna reduce fractions and stuff, at least I think it's probably good practice to write it out the way you're thinking about it, and then reduce it, or find a decimal on a calculator or whatever. Okay, so 1 out of 36. Okay, any questions about this? Okay, so I'll write this out a little bit more the way the book writes it out. So sort of in English, you might think of this as the chance that 2 events both happen. Is the chance of one of them times chance of the other given that the first happens. Okay. And when I do this, I also like to think also about the definition of probability, the way I stated it before in terms of long-run proportions. So you might imagine that everyone in the class has a red die and a blue die. And if you want to think about, well, what proportion of people would we expect to have both of these events occur? Everyone rolls the 2 dice. So one way you might think about it is, well, first of all, let's have everyone roll the red die. And all the people that roll a 1 on the red die maybe raise a hand or something, okay? So what proportion of people would we expect to raise their hands? About 1/6 of the class, right? Gets a 1 on the red die, raise their hand. And then, like the rest of the class we don't really care about. There's no way that the rest of the class could get the sum of the 2 dice to be a 2, right? So one way we could think about the overall chance of A and B is that first of all, you get that red die to be a 1, and then of the people that manage to get the red one to be a 1, what proportion of them do we expect to get the sum equal to 2? So those people require the blue one to also be a 1. So in terms of long-run proportions, you can kind of think about the same idea. And I don't know, I think it's sometimes, if you're a little bit confused or having trouble solving a problem, that is sometimes a good way to make it a little bit more concrete. Is imagine like a big room of people, and everyone's trying to do this. And you can kind of do it step by step to figure out what proportion of the whole class you would expect to get both those events to happen. Okay? All right. Questions? Thoughts? Okay. So let's see. Let's do one more example and then do break. Okay, so let me describe a standard deck of cards. You don't need to know what a standard deck of cards looks like. If I ever ask problems on a quiz or exam about a standard deck of cards, I'll tell you everything you need to know for the problem. But I'll just describe it. A standard deck of cards has 4 suits. clubs, diamonds, hearts, and spades. And it has 13 ranks in each suit. And the usual way to think about them is starting from 2, 3, 4, up to 10. So those cards all have kind of numbered ranks, and then jacks, queens, kings, and aces. Some games will treat aces as ones, but it's usually, for most games, it's the highest ranked card. So usually it's presented this way. So that gives you a total of 14. 9 of these numbered cards, and then jack, queen, king, ace gives you a total of 13. So 4 times 13 is 52 total cards. Okay. And I brought my big cards today, too. Very exciting. So this is a standard deck of cards, except bigger than most. So there's a bunch of numbered cards. Let's see. Let's find some other ones. So there's a jack. Right? The jacks, queens, and kings are pictures. There's a queen and a king. And the aces, like I said, in some sense, you might think of them as being ones because they have one thing, one heart. So the ace of hearts has one heart in it. On it, the four of diamonds has 4 little pictures of diamonds. So anyway, ace you might think of as either a 1 or just as the letter A. OK, so what I want to do is imagine like a shuffled deck. Imagine this is totally shuffled, totally random. And I want to find the probability of 2 events. The first event is the first card is a spade. So I'm imagining drawing the top 2 cards off the deck, right? So I'm going to draw 2 cards. I want to find the chance the first one's a spade and the second one's a spade. So probability of A and B. So when we see the probability of A and B, the way you might remember that you want to use the multiplication rule is by the word and. If you see the word and, or if you see something written like the chance that 2 events both happen, anything like that, or if you can kind of, if the question's worded in a strange way, if you can kind of change the wording to make it fit one of those 2 things. 2 events both happen, or chance of event A and event B. That's kind of a clue that the multiplication rule might be the way to go. Like I said, there are different ways to solve problems a lot of times. So it's not necessarily always true that that's the easiest. But generally, if you can phrase it like this, then it's nice to use the multiplication rule. So that's what I'll do. It says it's the probability of A times the probability of B given A. And again, I think it's nice to think about this in terms of a large class and long run proportion idea. You can think of this as sort of the proportion of people that we would expect to get a spade, right? So there are 13 spades out of the deck out of a total of 52 cards. So in terms of equally likely outcomes, that's going to be 13 out of 52. The second thing, this conditional probability, this is kind of like in a universe where event A has already happened. So it's as though you have already drawn the first card, and in fact, it is a spade, if I can find one. Seems like there should, yeah, there we go. OK, so there's a spade. It's like I've already got the spade to happen. So now, what's the chance of B given A? 12 out of 51. Okay? I've taken out one of the spades, so there are 12 spades left. Right? Originally, there are 13 spades out of a total of 52 cards. Now I've taken a spade out. I know the first one is a spade. And so there are 12 spades left out of a total of 51 cards. Okay? And that's multiplication. 13 out of 52 times 12 out of 51. Again, you can reduce those fractions if you want, but I don't really care. I'll do it. This is 1/4. I mean, you might also think about this as just all 4 suits are equally likely, right? So spades, clubs, diamonds, and hearts are all equally likely. So you might actually think about this as 1 out of 4. So 1 out of 4 times 12 out of 51 is, I guess, 4 out of 17. So multiply them together, you get 1 out of 17. Okay? So 1 out of 17 chance, in general, that you would get them both to be spades. It's a little bit different than 1 out of 16, right? 1 out of 16 would be 1/4 times 1/4. It's pretty close, but it's slightly different, slightly less likely. Okay? And essentially that's because once you've drawn a spade, it makes it slightly less likely that you'll get the next one to be a spade. Okay? So if we did it in the class, we would expect about 1/4 of the class to get the first one to be a spade. We expect about 1/17 of the class to get both cards to be spades. Okay? Questions? Thoughts? Yeah? She said, you always assume that you don't put the first card back. Well, I wouldn't think about it as an assumption. I would think about it as what I'm doing, right? If I'm taking 2 cards from a deck, I wouldn't even think about it necessarily as putting one back or not. These 2 cards are different, right? So it's not like I took one and then shuffled the other one back in and then drew another one, right? So if I say draw 2 cards off of a deck of, draw 2 cards from a deck of cards, I mean that I get 2 cards, right? Okay. So people use the words with replacement, without replacement. So what I mean kind of by default is without replacement, that I'm not, if I'm drawing 2 cards from a deck, I'm getting 2 cards. Okay, so they're different cards. It's not shuffled back in. Yeah? Okay. Any other questions or thoughts? Okay, so let's take a little break, and then we'll do some more stuff. Okay, let's get started again. So, I want to do a little bit more with the multiplication rule and conditional probability. And this is I'm going to have a kind of group exercise. And here are your instructions. You can do this with someone else, so you don't have to all use a piece of paper, but somehow I want you to either do yourself or have access from a friend to this. So tear part of a sheet. It doesn't need to be a whole sheet. Basically, you need to get 3 little pieces of paper that can, I don't know, be about that big. Okay? So if you want to just tear off the bottom quarter of a sheet of paper or something like that. So into 3 pieces. Okay, so like I say, you can share with someone, or you can tear one sheet into a few pieces and pass them around real quick. And label them. Label them RWB, so it's intended to be like red, white, and blue. Okay, so once you get your 3 pieces of paper, label them, fold them, mix them up. Pick one at random. And set it aside. Okay, and you can look if you want. But it really should be random, so it won't really work if you don't do it randomly. Okay, so I'll call that your first pick. And then out of the remaining 2, pick one. Again, you can look at it if you want, I don't care. This is your second pick. Okay, so this will work best if everyone does it. But yeah, so if you're not doing it now, but someone close to you is doing it, you can borrow their pieces of paper and you can do it too. Okay, so I'll give you a minute to complete that. Okay. Everyone all set? Okay, so no pressure, but I want to find out how many people didn't do it. Okay, so if you did not do it, I forgive you, but I need to have you raise your hand so that I know how many people did do it. So raise your hand if you didn't do it. Okay. So while we had our break, I counted how many people were in the class. That's why I need to know. Okay, so what I would like to think about, first of all, is the probability that the first pick is the R. Okay? What's that? What's the probability the first pick is red, or the R thing? 1/3, right? Okay, so. Well, let's see what happened in class. So there are 112 people, I think, that I counted that did it. I counted yeah, roughly, within a couple. So who got the red one first? Red one first. Okay. 2, 3, 4, 5, 6, 9, 10. Okay. I think you're lying. How many people did not do it? Let's try that again. 5, 10, 11, 15. Okay, the first time 13 people said they didn't do it, now 28 people said they didn't do it. So, okay. Again, I guess I have to forgive you, but okay, so I got 26 people that got red. So I'm going to call that out of 97. So it's still a little bit low. So I'm still suspicious, but let it go. So yeah, I counted 125 total people in the class. 28 people, I think, just said that they didn't do it. And I counted 26 people that said they got red ones. Let's do that again real quick. Red. Who got red? Who got red? Who got red? Maybe that's low. 3, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 25. Okay, so yeah, about the same. I'm suspicious about that group back there. Only 2 people in that whole section said they got red. Anyway, okay. Okay, so anyway, it's not super close, but yeah, it's not horrible. We'd expect about 32. It's a little bit low. It's not crazy low, but that is a little bit low. And actually, that tends to be what I see, is that I feel like not everyone responds, and so this number usually ends up being a little bit lower than the fraction that should be true. Okay, but I think it's interesting to just try it. Okay, so that's that. Let's think about the probability that the first one is red and second one is white. Okay, so what should this be if we do it as a probability problem? Sure. 1/3 times 1/2. It's the probability the first one's red. Times the probability that the second one is white, given first red. And the reason why I like to do this is it's very concrete. If you got the first one to be red, you have 2 choices left. One of them's white, one of them's blue. Okay? So the chance that, again, there are 2 possible outcomes here. One of them is white. This is 1/3 times 1/2. It's 1/6. Okay, so who had that happen? Who had first red, then white? Red, then white. Okay, so that's 14. So that's actually quite close to that. So in class, 14 out of 97. 14 times 6, I guess, is what? It's 84. So not too fast. I mean, not too far off. So this is in class. Okay, and what's interesting about this is, can you tell me what this is in the class? Probably the second one's white, given the first one's red. What's that fraction in the class? We would expect it to be 1/2, right? What do we actually get? Can you tell me based on what I have up here? What should we, can you tell me what the fraction is? This is a probability, right? It's a conditional probability of second white given first red. So you should be able to think about it as a long-run proportion. So what long-run proportion in the class should we compare to that? 14/26, right? It's of all the people that got the first one to be red, what proportion of them got the second one to be white? And I know that 26 total people got the first one to be red, and I know that 14 of them got the second one to be white. So if you wanted to, you could think about this as being like first red is like 26 over 97. This is like 14 over 26. Sorry, 14 out of 26. Multiply them together, you get 14 out of 97. Okay, which is what that is. So if you wanted to, you could think about it that way, just in terms of what happened in class. The reason why I bring that up is I think it's useful to think about this conditional probability as like restricting who you're thinking about, right? You're only thinking about the people who got the first one to be red. So that's sort of what you do when you do a conditional probability, is that it's necessary to have this first event happen. I don't care about all the people that didn't get the first one. I mean, I care about you. You know, you're all wonderful people, I'm sure. But in terms of this calculation, you know, I don't really care about all the people that didn't get the first one to be red. Right? All I care about is, of these 26 people, what proportion of them managed to get the second one to be white. OK. So that came out pretty close to a half for that part. All right. Which, you know, if you think about part of the issue with this 26 out of 97 is that some of these 97 people might be asleep and they might not be listening to any of my questions, or they might not raise their hand or whatever. But all these 26 people, well, they at least answered my first question, so I know they're at least out there and paying attention. So that might explain part of why this is closer to 1/2, and that this is considerably lower than what I might expect. OK, anyway. One more thing I wanted to do with this is find this. What's the probability the second one's white? Any thoughts? Yeah. Half? 1/3? Doesn't it depend on whether or not I replace it? Well, did you replace it? So I mean this in the context of what you did, right? If you follow these steps. So maybe some people will think 1/3, some people think a half. Those are sort of the common two responses. So this is 1/2, right? Probably the second one's white. Given that the first one's red, that's 1/2. Okay? One way I like, the answer to this one is 1/3. There are a couple ways I like to think about that. One way I like to think about that is this is not a conditional probability. Okay? I'm not given anything. This is out of the whole class, what proportion of people do I think got the second one to be white, right? And roughly out of the whole class, I think probably around 1/3 of you got the first one, about 1/3 of you got the second one to be red, about 1/3 of you got the second one to be white, about 1/3 of you got the second one to be blue. Those three things are equally likely, red, white, blue, for the whole class on the second draw, okay? So it's a little bit, I think this is a little bit non-intuitive because you might think about yourself. Well, for you personally, having already looked at the first one, the chance that you got the second one to be white is either 1/2 or it's 0. If you look at the first one and it's white, well then the chance you got the second one to be white is 0. If you look at the first one and it's not white, well then the chance you got the second one to be white is 1/2. And it might be kind of hard for you to sort of separate that out from your own personal experience. Both those things, though, are conditional probabilities. Probability that the second one's white given the first one's white, that's a conditional probability. It's given what happened the first time. And the probability the second one's white given the first one's not white, that's also a conditional probability. Tells you something about the first draw, first pick. Okay, so this is what's sometimes called an unconditional probability, or just a probability. And what I mean again here is it's the proportion. It's like the long run proportion of everybody that got the second one to be white. So just for fun, let's figure out what that is in class 2. So who got the second one to be white? Out of everyone who got this, yeah. 2, 3, 6, 7, 8. Okay, so I think it's 32 out of 97. Okay. So that's actually quite close, right? That's almost exactly 1/3. So whatever that's worth. That's what we saw. OK, any questions about that? OK, so if you want to, you can think about that 1/3. You can also think about it as some combination of the conditional probabilities. And I'll wait to do that until we do rule number 4, okay, which is the addition rule. Okay? So, questions about this? Sort of the end of rule 3, examples involving rule 3. But I will come back to this event if you want to, if you're not convinced or something. But I do like I say, I like to think about this in terms of just equally likely outcomes. Red, white, blue, all equally likely to happen on the second draw. So it's 1/3. OK, so the fourth thing is what's called the addition rule. So I'll describe this and do a little bit on it, and then I'll finish up on Tuesday. So the addition rule is used to find the probability of event A or event B. And I'll write down the formula first. Okay, so this is maybe the most, I don't know, maybe the hardest to get your head around, I think. So I'll draw a Venn diagram for it, which I think is somewhat instructive. So when I say A or B, in a probability problem, A or B means any time that event A happens or any time that event B happens. And I want to include the possibility that both might happen. So this is a little bit different than the use of the word or in regular English. In English, often we mean the word or to be sort of exclusive. If I said something like, I had a tuna fish sandwich or a burrito for lunch today, I probably don't mean that I might have had both, right? I probably mean, well, I either had a burrito or I had a sandwich. I don't mean that I had both of those. So there's a little bit different usage than what we're doing here. Here, when we're talking probability, we include the probability of both, or the chance of both. And it looks like we're not. It looks like we're getting rid of it by subtracting it. But let me explain and convince you that that's true. So if I write this in terms of a Venn diagram, two events, A, B. The probability of A or B, you can think of it in terms of areas, right? The idea of the Venn diagram is that, again, the total area is 1. So if I want to find the probability of A or B, I'm talking about everything in that thing, okay? So probability of A or B, you can think of as the area of this, okay? That sort of shape. So how can we get that? Well, we can get that by taking A and adding B, right? This, in terms of area, this is like that area, A. So again, A or B. This is A. And add on the area that's like this. But what's the problem with just adding those together? Yeah. Yeah, good. This counts the overlap part in the middle twice. If I just add these two together, that's too much. Right? This area of this circle plus the area of this circle includes this area in the middle twice. So I need to subtract it. And I'm only subtracting it once. Okay, this is this area that's like both ways, right? This is A and B. So I'm still including it in my overall area. I want to avoid counting it twice, right? So that's why I'm subtracting it once. By subtracting it once, I still include it in my overall area. And like I say, I just avoid counting it twice. OK? Questions on that kind of picture and intuition behind that? OK, so I want to mention here that the book presents the addition rule in a certain way. The book says that if you want to find the chance of event A or event B, check to make sure they don't overlap, okay? And the probability term for that is that they're mutually exclusive, meaning that if one happens, the other one can't happen. So the book says, check to see if they're mutually exclusive, and if they are, you can add the chances. Just do this. What mutually exclusive means is that they don't overlap, okay? So mutually exclusive, I'll talk a little bit more about this later, but I just want to point out that there's a little bit of a difference between the way that I am describing this and the way the book is. So mutually exclusive would look like this. Okay? There's no overlap, so in that case, it's perfectly fine to just say the probability of A or B is the probability of A plus the probability of B. In general, you have to be concerned if they overlap. And if they're, the correction is relatively simple, but the book doesn't do this. The book doesn't include this more general form of the addition rule. The book just says, if it looks like this, then the probability of A or B is just probability of A plus probability of B, okay? Sort of a special case of this. So I'll talk about that a little bit more later, but I just wanted to, mention that the book is a little bit different for this. Okay? Questions on this general idea? Alrighty, so. Let's do one example of this. Actually, I'm sorry. I meant to do one more thing before I do the addition rule. Let me back up and do it, and I'll come back to an example for this. I just want to, I want to mention this when the idea of the multiplication rule is still relatively fresh, and the idea is to talk about independence. Okay, so I'll just say intended to be before addition rule. So if you want to draw an arrow in your notes or something like that. Because this is not relevant to the addition rule, what I'm about to say. Okay? So apologies for doing that out of order. The idea of independence, I'll describe for two events. Oops, independence. So A and B are independent if the probability of B is equal to the probability of B given A. Okay? That's the usual way of writing it. It's equivalent to saying, and that's a definition of independent. So if they're independent, then this is true. If this is true, then they're independent. So equivalently, you could say the probability of A and B is equal to the probability of A times the probability of B. So that's, I think, fairly clear why those are equivalent. In general, the multiplication rule tells us that the probability of A and B is the probability of A times the probability of B given A. Okay? So if this is true, if probability of B is equal to B given A, probability of B given A, you could just put a probability of B in here instead of the given part. So intuitively, what I mean by independence is that the chance of an event is not affected by whether or not the other event happens. So chance of one event is the same if another event happens, and this other event A happens, okay? And this is a special case of the multiplication rule. Okay. So I want to do an example to illustrate this. This actually will go nicely into the example I want to do for the addition rule anyway. And I want to imagine two die rolls. So example, roll, red die, and blue die. and I want to find chance that I roll at least 1/6. Okay? So there are a few different ways to do this, and the reason I really like this example is that I can actually use any of the four tools that we've talked about. So the first way I'll do it is maybe the easiest, which is just to use equally likely outcomes. And it's not equally likely outcomes for one die, but it's all the equally likely outcomes for both dice. So I'm imagining the red die, the blue die, the outcomes in a big grid. 1, 2, 3, 4, 5, 6. If you want, you could think of this as a big Venn diagram. Okay, total area 1. It's a 6 by 6 grid. So each square here has area 1 over 36, right? 6 times 6, so 36 total squares. As a Venn diagram, it has a total area of 1, so each one of these squares has probability 1 over 36. And we could just count. If you want to roll at least 1/6, well, that means that either the red one's a 6, somewhere here, or maybe the blue one's a 6, here. So you can just count them. And there are 11 ways. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36. Okay? So again, you sort of think of this as just in terms of equally likely outcomes. There are 36 equally likely outcomes. 11 of them have one of the rolls be a 6, possibly both of them, right? Possibly they're both 6s. And so total chance is 11 out of 36. It's possible if you thought about this, you might have thought that this answer should be 2 out of 6, 1/6 plus 1/6, which is not quite right. Okay? That would be 12 out of 36, and I'll explain why that's not quite right in a second. Second way of doing this problem is to recognize that this has a complement. This event has a complement which is slightly easier to think about. Okay? At least 1/6 is what? No 6s at all. Either you get at least 1/6 or you get no 6s. Another way to say no 6s is that the red die is not a 6 and the blue die is not a 6. So the probability of at least 1/6 is equal to 1 minus the complement. The complement, again, is the probability of red not 6 and blue not 6. Okay. So and suggests multiplication rule. And these two events, red not 6 and blue not 6, those two events are independent. Whatever happens with the red die, that does not affect the chance that the blue die is going to roll a 6. Okay? So this is going to be 1 minus red not 6 is 5/6, blue not 6, also 5/6. Multiply that out, that's 1 minus 25 over 36. So this is 36 over 36 minus 25 out of 36 gives us, again, 11 out of 36. Okay? Okay, questions on that? Okay, one more last thing I want to do. This will be quick. This will be quick. Is to do the same problem using the addition rule. And this is basically an illustration of why the answer 1/6 plus 1/6 would be incorrect. So using addition rule, at least 1/6 is the same thing as red 6 or blue 6. Okay? If either the red one's a 6 or the blue one's a 6, then I got at least 1/6. Okay, so probability of red 6 or blue 6 is the probability of, I'm just plugging into the addition rule, probability of the first event plus the probability of the other event, blue 6, minus the probability of both. OK? Both 6s means the red one's a 6 and the blue one's a 6. So that's going to be 1/6 plus 1/6 minus red 6 and blue 6 gives me 1/6 times 1/6. So this is 6 over 36 plus 6 out of 36, 12 out of 36 minus 1 over 36 gives me 11 out of 36. OK? So same answer, yet a different way. And I just want to really quick point out what's going on there in terms of the addition rule. What's happening is I'm taking this 6 over 36 here plus 6 out of 36 here. But the problem is that that counts this twice. To avoid the double counting, I need to subtract that once. This is the probability of A and B, the probability they're both 6s. Subtracting that once to avoid double counting gives me the same answer. OK, sorry to go just a tad over. I'll talk a little bit more about the addition rule on Tuesday. And then we'll do chapter 15, which is on the binomial. OK, bye. Have a good weekend.